Why does evolution matter now?
Evolution matters now because it happens every day in our lives. A perfect example for looking at this is in sicknesses, which are caused by microbes. Microbes are small particles that are able to cause disease in human beings. They include things such as bacteria, viruses, mycobacteria, fungi. And their evolutionary world in which they try to survive is inside the human being.
Viruses, bacteria, and other microbes may be all but invisible to us, but that doesn't mean we don't play a huge role in their evolution. The way we use antibiotics, for instance, has a lot to do with which ones survive, the helpful ones or the harmful ones. Tuberculosis, the leading infectious killer of adults in the world today, is caused by bacteria, and it has become one of the most lethal, especially in Russia, where evolution on a cellular level has resulted in some tuberculosis bacteria that are resistant to drugs, threatening the survival of hundreds of thousands. This is ground zero of a global tuberculosis epidemic. Russia's crowded prisons provide a perfect breeding ground for the transmission of tuberculosis.
Tuberculosis is spread through the air and is therefore a very threatening disease in that someone could cough and a few hours later someone walking into that room could inhale the air and become sick with tuberculosis.
People who do become sick with tuberculosis develop a cough and fever and begin losing a lot of weight.
If you look at the X-ray of the healthy lung, what you see is a lot of dark areas within the lung. That's because the lung is primarily composed of air, and that indicates that there's a healthy lung. When you look at the tuberculosis lung, you can see that there are many white areas. What's in there is a lot of phlegm and blood and pus. The person is constantly coughing this up when they cough, and it's a sign that the person is quite ill.
Like Dr. Jennifer Furin, microbiologist Alex Goldfarb is one of the many health professionals who travels from the United States to Russia to combat multi-drug resistant TB.
Every one of you has been diagnosed with multi-drug resistant tuberculosis. In other words, the type of tuberculosis that you have does not respond to regular medications.
When people are sick with tuberculosis, we often need to give them more than one medication in order to kill all of the bacteria that are living within inside that person.
Treatment begins with one medication. The antibiotic kills many of the bacteria. A second dose of the antibiotic kills off even more bacteria, but still some remain alive, resistant to the antibiotic. If the patient does not take all the prescribed antibiotics, these resistant bacteria multiply and pass their resistance to their descendants, and the patient remains sick. In this way, a strain of bacteria evolves to become fully resistant to an antibiotic.
And the same cycle can continue until the person is resistant to all the medications that we use to treat tuberculosis.
It's a classic example of natural selection. Genetic variation within bacteria strains allows some bacteria to survive even when hit with antibiotics. These surviving bacteria are selected and continue to evolve. That is, survive and reproduce over time, unless treatment is thorough. A single bacterium can reproduce 1 million times in a single human lifespan.
It would be impossible for me to do my work with the sufferers of TB without understanding how evolution works, because evolution is key in how we treat and understand the disease.
So why should we be concerned about how evolution happens in a prison halfway around the world?
Globalization is not just, financial markets or the information space, which became global. The bacterial ecology has also been globalized.
We recently heard about a gentleman in Russia who was very sick with multi-drug resistant tuberculosis, and treatment was not available for him in Russia at the time. He boarded an airplane and flew from Moscow to New York City, went straight to a hospital there to get treatment for his multi-drug resistant tuberculosis. But in the setting of being on the airplane, he had coughed, the air is recirculated, and 34 people were infected with tuberculosis on that one airplane flight.
In the United States, about 10 to 15 million Americans are infected with TB bacteria, and at least 1 million are expected to develop the disease. Evolution matters now because what happens to bacteria in a Russian prison can happen closer to home, as we use antibiotics in our doctor's offices, clinics, and hospitals. Our very survival depends on our understanding of evolution.
If we can drive microbes to evolve drug resistance, then we can also make them evolve in ways that benefit us. This is the radical proposition of Amherst biologist Paul Ewald.
When people are looking at the antibiotic resistance problem, they see evolution as sort of the bad guy. It's the evolutionary process that's led to antibiotic resistance, and that's true. But just as easily, we can have evolution being the solution. In other words, we can have evolutionary processes leading to organisms becoming more mild.
Disease organisms evolve to be more or less harmful depending on how they are spread. Microbes that depend on close contact between people tend to be mild.
The rhinovirus that causes a common cold is transmitted by people walking around sneezing or coughing on other people. Since it really does depend on fairly healthy people to be transmitted, not surprisingly, it's one of the mildest viruses that we know about.
But microbes that are transmitted by insects or by tainted food or water tend to make people very sick.
The worst of all of the diarrheal bacteria that we know of have been waterborne. The bacteria that cause cholera and typhoid fever are often waterborne. So even if the organism is so harmful that the sick person can't move from bed, the organism can still be transmitted to large numbers of people. Once we understand the factors that favor increased harmfulness and decreased harmfulness, then we can look at all of the things we do in society. And we can ask the question, are we doing certain things, or can we do certain things, that would favor organisms evolving towards mildness? We can look at the cholera outbreak in South America as a kind of natural experiment that allows us to evaluate these ideas.
In 1991, cholera invaded Peru and spread quickly. Over the next 5 years, more than 1 million people were stricken with diarrhea and vomiting, some severely. Over 10,000 people died. The disease was transmitted through water contaminated with human waste, or through food that was washed or handled by infected people. Ewald collected strains of cholera bacteria from South America and measured the amount of toxin they produced, an indication of their virulence. Over time, he would document evolution in action.
If you have contaminated water allowing transmission, we expect the cholera organism to evolve to a particularly high level of harmfulness, and that's exactly what we see. We find that bacteria that had invaded countries with poor water supplies evolved increased harmfulness over time. They've actually become more toxigenic. They produce more toxin than they did at the outset. If instead we clean up the water supplies, then we force the bacteria to be transmitted only by routes that require healthy people. And what we find is that when cholera invaded countries with clean water supplies, the organism dropped in its harmfulness. Those bacteria evolved lower levels of toxin production. They actually became more mild through time. People would still be getting infected, but the infections would be so mild that most people won't even be sick. So the cholera outbreak in Latin America suggests that we may need only a few years to change the cholera organism from one that would often kill people to one that hardly ever causes the disease. What we're suggesting here is that we can domesticate these disease organisms very much in the same way that we've domesticated other organisms that are potentially harmful.